Hey programmers, welcome back. Right now I want to go over a Python solution for this tree levels problem. So I'll jump right in and I'll show you a bunch of different ways to solve this one. So why don't we start with maybe some iterative renditions. What I'll do is maybe do a, we'll say depth first iterative piece of code, right? So we'll start with, of course, our stack. So I'll say stack equals, and I'll just use a Python list because I know if I just remove from the end of a list and add to the end of a list, those just run in O of 1 time. So a list is fine if you're doing a stack order. One thing I do have to note here probably is they don't really tell us that I can assume that the tree is non-empty. If I look at some of these test cases, the very last one is they pass along a none node to begin with. So I'm going to have to actually guard against that explicitly. In the case of my top level root being none, I don't want to just initialize my stack with a none, right? In general, I want to store basically nodes as elements of the stack, not none pointers, right? So up front, I'll go ahead and check. All right, if root is none, then just bail out and return an empty list. Remember that here in this problem, we want to return a list representing all of the levels, right? Technically, the elements of that list would be other lists, right? An individual sublist represents a level of our tree. Nice. But in any case, back to our code. If I have a root that actually exists, then I can do a depth first traversal through it. So I want to iterate while my stack is not empty. So I'll just say while stack. And I'll just start to write my basic code for a depth first traversal. But one thing I have to keep in mind is in the long run, I want to accumulate all of my node values into a 2D list, right? So I'm going to create that list over here. I'll call it levels. And by the end, I'm going to return it. So something like this, return levels. But how would I know, like, at which level do I put these different nodes, right? How would I know that, all right, the root of A goes in this first subarray. The node of D goes in this last subarray. You need to basically track what level you find each of these nodes at. And I know that, all right, the root node has a level of 0. And so what I can do is maybe just add some like meta information to my stack. So instead of just storing the root, I also want to possibly store its level. So I'll say root comma 0. So what I'm storing as, I guess the elements of my stack now, I'll call it a stack frame. What I'm storing now is a tuple, right? Containing as the first element of the tuple, the node. The second element would be the level that I found it at. So the root has level 0. Cool. So if you're unfamiliar with tuples in Python, a tuple is basically just a sequential collection of things, almost like a list, except a tuple is immutable, meaning you cannot make changes to a tuple, which is okay because I won't need to do that, I think, in this problem. But how do I structure my code now? Well, in general, I know I must remove the top of my stack, so I can say stack.pop. And this would actually now give me back a tuple, right? A pair of things from the stack. So if you wanted, you can save it as like, I don't know, your like current. But if you did that, that would technically be now a tuple. Maybe off the bat, I can unpack them. So I can say, I know this expression gives me back a tuple. I can just unpack them immediately and I say, the first thing is going to be my node. And the second thing is going to be my level num, we'll say. So on the first iteration of this while loop, node will contain a reference to the root instance of node, and then level num will be 0. And then from here, I can start structuring my generic depth first code. So I want to look at the children of this node and see if they exist. So I'll check if node.left is not none. Then I need to add them into the stack. So something like stack.append. But I don't want to just do this, because then you'd have inconsistencies in your data, right? Because this would be adding a instance of node directly on the stack, whereas it looks like initially it should just contain tuples, in which inside one of those tuples the node is. So I want to have a consistent type here. So instead, append a tuple where the first thing in the tuple is the node, and the second thing is the level. And how do I derive the level of the left child? Well, it's just +1 compared to the level num of the parent, right? So over here I can say, all right, that left child is now going to be tagged with level num +1, just like that. Cool. It's just going to be symmetric for the the right child. So we'll say right. Awesome. So that code is looking pretty good. And so far, this just does the correct traversal, but I'm not really contributing anything into the levels array, right? So I'll do some theory over here. How do I know whether to create a new sublist of levels or to add to an existing sublist? What I would do is just plug in mentally some actual concrete values, right? So let's say we're stepping through, I don't know, test 0, 0. And we know that our tree would be this one, right? And let's say we're on the very first iteration. We would have just removed the A node from our stack. We know that the A node would have a level num of 0, right? Technically at the beginning, we know that our levels would be just an empty list, right? And what I can do is, this is actually the occasion where I have level num at 0, but there is no subarray at index 0. Right? Index 0 would mean there is at least like one thing inside. So one thing I can do to check here is just, all right, if the length of your levels, if that is equal to your level num, then you need to actually create a new subarray. So I can say levels.append. So append a brand new level and just throw in your node value, just like that. And how does this work on the first iteration? Well, I know I just removed the root of A from my stack. Its level is 0, and I check. The length of levels is also 0, right? This is true, and so I append a new subarray, just write like this, containing the value of A. And now I've technically made it such that the length of levels is 1, right? So that looks pretty good. And now in the else case, that means that the length is already kind of what it needs to be. So I could just append to an existing level. So I can say levels, square bracket, level num, and append just the node value, just like that. So that's looking pretty good, right? So let's say we kind of hop to the future, right? So I'll add some comments here. You're probably wondering, how does this else statement work maybe? So let's say I'm at the point where I just removed, let's say, E from my stack. If I removed E from my stack, then that must mean you already hit A, B, and D. So they should be in their respective subarrays. So A, B, D. And remember, these indices should align. This is level 0, level 1, level 2. Right? So let's say I just removed E, right? So I know that my node is E, and its level num must be 2, because I go 0, 1, 2, right? And so I'm going to check, all right, what's the length of levels? Right now it's 3. And I check, is 3 equal to 2? That's false, so I run this else statement. That must mean that level 2 already exists within my subarrays. And so I just say levels square bracket 2, and I append my E into index 2, 0, 1, 2. I add E right here. And that's good to go. That's eventually where I want to put the E node. Nice. So I'm feeling good about this pattern. Yeah, I think let's just go ahead and run the code. I think we'll have one thing off, but we can fix it together. If I take a look at my expected output, we're almost there. If we look at the expected and the actual, right? The actual is what my function returned. Ooh, it looks like my levels are just in reverse order, right? I want BC, I gave back CB. Likewise for this other level here. And that makes sense because technically, I think in my code, I made a little mistake here. This is definitely a depth first, which is okay, but I push the left and then the right. Remember that we're using a stack here. So if you push the left and then the right, that means the right node is on the top of the stack, which means on the next iteration, you'd be preferring to iterate through your right child before your left child. That's why my code flows right to left. But I really want left to right, apparently. So I'll just flip the order of these. Now I'm guaranteeing that the left node would end up at the top of the stack, so it would be explored before its right node. So should be aware of how to manipulate the left to right versus right to left order there. We'll run that again, see what we get. Cool, and there we have a nice iterative solution for our tree levels problem. So let me show you some quick variations of this. And they would basically all have the same runtime. So I think the easiest transition now would be to a breadth first iterative, of course. And so we'll start by renaming stuff over here. So I'm going to call this my queue now. And I want to do this in an efficient way. So like I usually like to do, I'll say from collections import deck. That way I can get constant time removal from the front of my queue. And I'll initialize my deck like this. Yeah, this looks good. And when I remove the front, that should be a pop left operation now. And I'll add to the back. So that all looks well and good. And I want to stay focused again. I want to make sure that I still do a left to right traversal. But now that I'm using a queue, right, I know queue is first in, first out. So if I put the left before the right, that would mean that the left would leave first, which would give me a left to right traversal breadth first style. So I'll run this. This might be our breadth first implementation of it. Awesome. Very, very trivial changes here. And finally, let's go through my favorite solution. All of you by now probably sense that I am partial to recursion. I don't know why. I just like it. I think it ends up being pretty elegant code, but I always say that, right? So let's start by defining our tree levels function again. And to structure this one recursively, what I usually do for this pattern is I use like a helper function to actually perform the traversal. So I'll create the helper over here. I'll call it maybe fill levels. And how do I want to actually like use this function? Well, I still want to create a levels list that will end up as like a nested list, right? And I'm going to use the fill levels to actually perform the recursion. I'm going to give it the root initially, but I'm also going to give it a reference to the levels list. What I want this function to do, this fill levels function, I want it to actually mutate that levels list. So if you're unfamiliar in some Python, if you pass in any like non-primitive type, you're going to get it by reference, which means if I take in the root here, I also take in the levels. If I, let's say, appended any elements into this levels list, it would affect this one, right? Cool. So kind of just stubbing out my main function. I do want to, at the end, return levels, right? But now we have a lot of work to do within our recursive helper function. I know that this function still needs to track like level numbers, because how would it know which subarray to put different values at? So the pattern I can use there is have this taken a third argument, maybe call it level num. And when I make my top level call, what should I pass in as a level num for the root? Well, we know that the basis is always 0, right? The root has a level 0. And that would tell me exactly which subarray to put it into. But for now, let me lay down my core recursion. So as always, right? Your recursive code probably going to catch if your root is none, then you don't really need to do anything, so just return. Otherwise, you need to recurse, so call your same function on your root left, and levels doesn't change. But for your level num, what I know is if a parent node has level n, then its child has level n plus 1. So I can just do level num plus 1, and that feels very reminiscent of our other code down here, right? Just kind of translating it for a more recursive point of view. Just going to be symmetric for the right-hand side. So this is doing the traversal, and it's, I think, passing the correct level numbers, but it's doing nothing yet with the levels list. So I think I just want really the same pattern, right? So if it's the first time I'm seeing this level, then I'll create that new subarray, this new sublist. If it's a subsequent time I'm seeing an existing level, then I'll just append to the existing sublist. So just this code will be about the same. And of course, I'll rename this to root val. All right, so should feel very familiar, although now it uses some recursion. If I do a quick spot check, since I'm doing my root.left call before my root.right call, I'll travel through the left child before the right child, which does give me a left to right traversal. Always a little tedious to think about that one. So let's run this, see what we get for our recursive version. And I believe, yeah, there we have it. So many different ways you can implement this tree levels problem. I do consider this a core pattern, and it would make me very happy if you actually practice all three, right? For some future problems, sometimes I find the iterative more useful, sometimes I find the recursive more useful. So it's okay to practice all three and then just have a favorite that you're like really proficient at coding up in the future. But I think there's a value in looking at different ways to implement these patterns. I think the most important thing you should take away is though, right, the root has level 0, and in general, if you have a node with level n, its child has level n plus 1. So with that, practice this, and I'll catch you in the next one.